All righty. So this problem here, we're going to do two different things to. We're going to try and figure out how resistance changes with temperature. So we're gonna start with just doing this the way the textbook does it, where we treat our alphas as constants. However, I know there's a few people who will notice that the table in the chapter says that that is the alpha at 20 degrees Celsius. So when you're doing assignments and whatnot, you just use the alpha that's on that table. I'm not real concerned about what the temperature span is, but we are going to look at, and I'll show you why we're going to treat our alphas as a constant. I'm going to show you what happens to this problem if we take account of how the alphas change based on temperature. Because one of the reasons it's important is you see here, these are thermometers that use semiconductors. But if you have a patient that's too warm or a situation that's too warm, what happens to a semiconductor if you heat it up too much? Turns into a conductor, completely destroys the reading. So we can't always just take these alphas, these constants, these unique numbers for a material as always going to be constant. Again, when you're solving homework problems for a 100 level class, just use what's on the table, but I'll show you what happens otherwise, because we are using germanium. Okay, and we know that on that table, the alpha for 20 degrees C can anyone tell me just by looking at the alpha what kind of material germanium is? Most of the alphas on there are positive. You have three of them that are negative. This means that your resistance will be decreasing as temperature goes up. So what does that make germanium? Not an insulator. Somewhere between the two. Semiconductor. Okay, so do what? No, that's alpha, not fish, alpha. I feel like we should have a quiz where I ask you about letters of the Greek alphabet. Fish. Proportional to cannot be fish, alpha cannot be fish. They're not the same thing, so they can't both be fish. Okay. Should know lambda. That's wavelength. You know mu, yeah, that's micro. So what is the resistance of this thermometer at 40 degrees Celsius? So again, what the problem says here, treat alpha as a constant for simplicity. That's as far as we're really going to go for a 100 level class, but I will show you how this breaks down otherwise. So first off, remember our resistivity equation is this. But the equation we're going to use is this. Does that work? Well, the resistivity version, and then you have the resistance version. Can I just write down the resistance version like that? I just want to know if you can tell me if if the resistivity equation yields the resistance equation. Yeah. No, it's just one equation becomes the other one, does it? Right, it's by L over A. So if I put in, no, let me make this easier to read. You see, I can divide out the A over L and I end up with the resistance equation. So we can do, so this, the textbook has the one for resistivity, but we can just go ahead and put in resistance. Rho is your resistivity. So then the way we're going to solve this is, what is our resistance? All righty, so we have resistance R at 37 Celsius. What is the resistance at 40 Celsius? So we can say, we're trying to figure out the resistance at 40 Celsius. R is going to be our resistance at 37. And then, even though we're not at 20 Celsius, we're going to go ahead and put in the and then our delta T. So your resistance at 40 Celsius becomes 0.85 R. So you can actually see some of the semiconductor behavior developing because resistance is decreasing with temperature. Now, granted, this kind of bugged me because it's like, well, with that alpha specifically for resistance at 20 degrees Celsius, how would we then start to translate that? Well, we have to figure out how alpha changes based off temperature. So I'll do this in a different color since this is just kind of, well, it's just kind of like, what's the real situation here? So this is where, so that first part there, that's the problem for the 100 level. We're going to bump this up to like a 200 level, see if we can figure it out. So what I'm going to say, I'm just going to set some T0 at 0 degrees Celsius. So then I know R at my new temperature. So RT is pretty much going to be at 40 degrees. Just keep putting that as T0 so we don't get confused. Okay, we have that one. Now we also are specifically looking for that difference between 20 and 37, so then 37 to 40. Because we want to know the alpha at 37, so we could actually use that. Because again, we can use these equations over and over and over again, just putting the right number in for the specific temperature. And this is, we're going to relate that to RT0. The reason we can do that now, what we do with that, we're going to put this into here. So what we're going to do now is solve for our new alpha at T0. So we know we can have a generalized RT equation. Because if we're able to relate the 20 degrees to T0, what else are we able to relate it to? These equations where your resistance or resistivity is based on temperature can relate what? Does it have to relate to specific temperatures? No, it can relate any two temperatures. Now, there's a number of ways you can go about this. This is just the way I did it. I said that we're going to relate the 20 to RT0. We're also going to relate it to RT. So just any temperature. This pathway made the math easier. All righty. Now, I can divide out the resistances. Now, here you could go ahead and factor those two together. That's going to end up giving quite a bit of algebra to do. I decided to use another one of our little physics tricks to make this easier on myself. So what we know, we have a system of T's, T0s, and 20s, 20 degrees Celsius. So what can I do? So on the left side here, what I'm going to say, it's going to be 1. And here I'm going to have T minus T0 plus D0 minus 20. And this will actually work out to make things quite a bit easier on us. I chose this route over factoring the right side. But if you're a stickler and you really want to foil the right side, you go for it. Okay, so what I'm going to do is now I'm going to divide through and divide through by that factor right there. Okay. And then I can split this center section up. Now on the left, I have to split the fraction. Does anyone remember how to split fractions? No, they both have, so it's a single denominator, so I can just split it at the plus sign. Yep. So this one here becomes 1. All right, well, I can just subtract 1 from both sides. And so I'm going to subtract 1 from both sides and flip everything around. So that's going to give me all right. Then I divide through by T over T0. And I get an expression on how to convert alpha between 2 different temperatures. Or at least in this case, I specifically was shooting for between 20 degrees and whatever temperature I'm looking at, because our table has our alphas at 20 degrees. Okay, so now this, of course, and this alpha can, of course, then be generalized to any temperature. Okay, so what we can do is that we can say, well, what happens to the alpha at 37 degrees? So let's see, 1 plus our alpha at 20 degrees. We have 37 minus 20. On the top, we have our negative 50. So when we calculate this, alpha is going to be a negative 0.333 inverse degrees Celsius. So now we have a new alpha that we can actually plug back into our original problem. So what's the resistance at 40 degrees? Well, it's going to be the resistance at 37 degrees. Remember the resistance at 37 degrees, they just called R. And we have one alpha 37 degrees, and we know our temperature difference is 40 minus 37. What we actually get is the resistance of the germanium thermometer at 40 degrees is 0.001 R. So originally what we calculated was about 85% of the original R. In reality, this small temperature change, this 3 degrees Celsius temperature change, has crossed the regime from resistor to conductor, or insulator to conductor. So again, for problems in this textbook, we're just going to use the table that's there as constants. But in reality, this would not be a good time to use the germanium thermometer because it's going to short circuit. The germanium has crossed the regime into conductor. So if I was to bump this up to like a 200, a 220 level, we would do this, like this is where we would go with it. As it stands, you're only going to be responsible for this first part. But we notice that 85% of our is actually quite a far ways off. The point is just trying to get across the point that for these semiconductors, as temperature goes up, resistance is going to decrease drastically. Now, if you were in a real situation and you weren't aware that the material inside of your device was a semiconductor, you could, like, someone could get hurt, you could destroy the machine, all kinds of stuff. And so you could actually generalize this if you wanted to. Alpha at any temperature going to be 1 plus alpha at your initial temperature so you could generalize that to any two temperatures. I felt like this was a good thing to do before we hit Kirchhoff's loop rules, because every year people complain about Kirchhoff. After this, I don't think anyone will complain about Kirchhoff. Okay. And so for those who know, these next couple of slides are going to be telling a story. So now we're talking about resistors. So we use the little zigzag line as our symbol inside of a circuit. Most of you have probably seen that little device on the left. Those are the resistors you would see on your computer circuit boards or any piece of tech you open up. Those little wires be soldered to the board. These are going to resist current flow. And you should be able to tell how many ohms this resistor is by the bands on it. Now, that's just not part of physics, but these colored bands are like universal. So anyone from across the world should be able to look at those and say, this is a so many ohm resistor. Your main equation here is going to be V equals IR. So in this case, it's either V for volt, it's voltage. You could replace that with delta V if you wanted to, if you needed to. It's going to be the same equation. These delta V's are going to be important as we move forward into Kirchhoff's rules. Because if I have across a resistor, I have the voltage as I times R. What is the voltage? So what would V be for a battery? What is V equal for? No, not the unit. So I times R, what's I? Current. So current times resistance for a resistor is your voltage. Across the battery, what do we call voltage? Nope. It's a single symbol. Mm-hmm. EMF. Yeah, electromotive force. Yeah, no, some of you, when I every now and then I'll get an assignment where instead of a sigma, I'll get that. I was not going to call you out, but the weird why. Oh, the phi? Oh, gamma. You need to wear your glasses. Well, you could just start writing it like this. Just start doing that. Okay, well, now, one of the things we're probably going to, that we eventually are going to have to start taking account of is, I mean, for a system where there's no current, your voltage across your battery is just going to be your EMF. However, when a current is flowing, the voltage decreases. It's, your delta V equals your EMF across the battery. When there is a current, voltage is going to decrease across the battery. So, I don't know, the way we've been drawing circuits, and this is the way you'll continue to draw them, but just so you know, there's a difference. So imagine we have a resistor. So let's see, we'll go ahead and do, nope. So most of the time you'll draw your circuits like this. However, keep in mind, sometimes we're going to have to calculate the internal resistance of a battery. So we can draw two different connection points for the battery. Okay, so that little dotted line represents our battery itself. So from the for the first one up top, it expands into the one on the bottom. The one up top, that battery is that battery there is the whole dotted line system. So some batteries are going to have internal resistance. So that's your external, that's your internal. Still have your EMF. And then you're going to have I mean, I would try to keep them separate so you know which each one is. Usually load resistance is a capital R. Speaking of which, that would be a good term for a quiz. If you're working with circuitry, what is the load? The load. The battery feeds energy to the load. Yeah, so it's the circuit. It's a circuit that needs to be powered by electric current. Mm-hmm. Because it's a vocabulary word. Yeah, so it's the part of it's this it's circuitry that needs to have an external power source. Yeah, so the big R is the load resistor. Internal resistance of the battery. Mm-hmm. No, it's the same battery. You can think of it like this. No. Let's go ahead and work through a problem. Okay. Battery has a terminal voltage of 12 volts when no current flows. Okay, what letter would I associate that with? The terminal voltage. What do you think terminal means? So it is the EMF. The term in circuitry, terminal does not mean the end. Terminal means the terminals of the battery. What do you get? What voltage do you get when you stick that battery in a circuit and the terminals are connected? It has an internal resistance of 2 ohms. And a 1.0 resistor is connected across the battery terminals. Mm-hmm. What is the terminal voltage? Let's see. Let's see. I didn't notice that the textbook wrote this wrong. It says 2 things for terminal voltage. So we're just going to cross that out. And we're going to do this. So basically, it's like, what does the terminal voltage become when current is flowing? Okay. So that's what it's asking. Because remember, we said that the voltage will decrease due to internal resistance of the battery, or when a current is flowing. Okay, so we have a couple of equations we can use. We have that for voltage. We also have this. Here we can say I is V over R. All right, so let's pull everything with a V to the same side. So we're going to have V R over R. So then if I factor out a V, you get 1 plus R over R. So my new voltage is going to be this. So then from here, let's see, I'm going to have 1 plus 2.0 over 1.0, my EMF, 12 volts. So my new terminal voltage becomes 4 volts once current starts flowing. And then the current so my new voltage. So the math is easy, 4.0 volts per ohm. What is a volt per ohm? Nope. Who said it? Yeah, it's amperes. Okay, so far the math for these is not too bad. Now, Kirchhoff's rules, you're going to have to use multiple equations to figure out multiple variables. So like, for example, if I have 3 variables, how many equations do I have to have? 3 at a minimum. If I have more, it's just going to help. But if you have 3, always remember, count the number of unknowns you have. You have to have that many equations to solve. And thus the story ends. I don't even think most of you got the story. Yep. It's a whole story. Okay. Kirchhoff's rules. So the 2 main rules you're going to be looking at, the sum of the currents entering any junction must equal the sum of the currents leaving that junction. Does that make sense? Yeah, so it's conservation of current. So the way we can look at this, yes, anything vocabulary based would be a good quiz question. I don't know, it's on the syllabus. And then let's say we have a split here. So we have a junction. This starts out current 1 leaving the battery. At the junction, it's going to split into current 2 and current 3. So what Kirchhoff's rule is saying is that I1 must equal I2 plus I3. So that's the conservation of current. That's that first rule. And so we'll pick up here on Wednesday again and work through and start solving problems with Kirchhoff's rules.